Welcome to The Explainer. Today, we're going to break down a concept that is, well, literally all around us. It's in the dashboard of your car, and it's at the very heart of calculus. We're talking about how things change.
All right, so let's kick things off with a question. And it seems super simple on the surface, but it's actually pretty deep. You know, we can all figure out our average speed on a road trip, right? It's just a total distance divided by the time it took. But what about that little needle on your speedometer? It's telling you something completely different. So what is it actually measuring?
Okay, so to really get to the bottom of that, we first have to get crystal clear on the fact that there are two different kinds of speed. You've got one that's like the big summary of your whole trip, and another that's more like a single snapshot in time.
So first up, let's talk about average speed. This is the one we all learned back in school, right? It's the big picture view, just the total distance you went divided by the total time it took you to get there. Simple.
For instance, let's say you drive 20 kilometers, and it takes you exactly half an hour. Well, your average speed is a nice, round 40 kilometers per hour. Pretty straightforward, yeah?
And this is where we see the key difference. Look, on the one hand, you have average speed, which is looking at that whole chunk of time, say from 10 to 10:30. But then you've got instantaneous speed, and that's all about zooming in on one specific moment. What's happening right now at exactly 10:15.
Okay, and this brings us to a really fascinating problem, a little conceptual hurdle, you could say, because that simple formula we have for average speed, it just completely falls apart when we try to measure speed in one single instant.
I mean, think about it for a second. That average of 40 kilometers per hour, it doesn't tell you the whole story, does it? At exactly 10:15, were you flooring it to pass a truck? Or maybe you were slowing down for a turn. The average it smooths over all that interesting detail.
So here's the real issue. To find the speed at one precise moment in time, our trusty distance over time formula just breaks. Because what's the time interval? It's 0. And, well, you can't divide by 0. It just doesn't work. We need a totally new way to tackle this right now problem.
So how in the world do we solve it? Well, not with another formula. We solve it with a picture. That's right. A simple graph of our journey actually holds the key to unlocking this whole idea of instantaneous speed. It's actually a 4-step process. First, you just draw a graph. Distance on one axis, time on the other. Step 2, you find the exact point in time you're curious about, say 10:15. Now here's where the magic happens. Step 3, you draw a straight line that just kisses the curve at that one single point. We call that a tangent line. And then, for step 4, you just calculate the steepness, the slope of that line. That slope is your answer.
And that right there, that is the big aha moment. The steepness of your graph at any point tells you exactly how fast things are changing at that very instant. If the line is super steep, you're going fast. If it's kind of flat, you're going slow. That tangent line is the perfect tool for measuring the steepness at one precise spot.
All right, so what we've just done with a picture, this clever little visual trick, it's time to give it its proper name. Because this is actually the core idea behind one of the most powerful tools in all of mathematics.
You see, this whole process of finding the slope of that tangent line, it isn't just some neat trick. Nope, it's a fundamental operation in calculus, and it has a formal name. And that name is differentiation. Think of it like the mathematical engine that's built to do exactly what we just did visually. It's the tool that lets us find the precise instantaneous rate of change at any given point. It's the solution to our right now problem. Okay, so we've figured out how to measure the rate of change for one thing. But what happens when you have a whole system of things that are all connected? You know, like a domino effect? How does a change in one little piece ripple through the entire system? Let's build a really simple system to see exactly how this works. Imagine you have a variable y, and it changes 3 times as fast as another variable u.
Okay, now let's add another link to the chain. What if that variable u changes 5 times as fast as a third variable x? So u depends on u, and u depends on x. You can already see this domino effect taking shape, right?
So the big question is, how fast is y changing compared to x? Can we find that direct link between the first domino and the last one, without even worrying about the one in the middle? And the answer is a big yes, thanks to something called the chain rule. Now, I know that calculus notation on the right looks a little scary, but just look at the logic on the left. It's so simple. If y changes 3 times as fast as u, and u changes 5 times as fast as x, Well, it just makes sense that y is going to change 3 times 5, or 15 times as fast as x. You just multiply the rates together. That's all the chain rule is. It's just a formal way of linking those rates together.
All right, so let's do a quick recap of everything we've just unpacked. We started by seeing that average speed and instantaneous speed are two totally different ideas. And that speedometer in your car? Yep, that's measuring instantaneous speed. We figured out we can find this speed visually just by using the slope of a tangent line on a graph. And we learned that the fancy calculus tool for doing this mathematically is called differentiation. And finally, we saw how the chain rule helps us connect all the dots when a whole system of things are changing together.
And this all leads to a final, really powerful idea. When you think about it, from economics to ecology, everything is connected by these rates of change. And that leaves us with a pretty cool question to ponder. If the rate of change of one tiny thing can affect an entire system, what are the chain reactions that you're a part of right now?